Ladies and gentlemen, thank you very much for coming to attend our press conference despite your busy schedule. Let me introduce myself. I am Mayaguchi from Communication Section of Inamori Foundation, serving as MC today. I ask for your kind cooperation. Now, let me introduce the members for this conference. First, from your left, Chairperson of Kyoto Prize Executive Committee, Dr. Hiroshi Sakaki, Fellow at Toyota School Foundation. I'm Sakaki. Nice meeting you. Next is Chair of Kyoto Prize Committee of Advanced Technology, Dr. Hideyuki Tokuda, President of National Institute of Information Technology. I'm Tokuda. Nice meeting you. And next is Chair of Kyoto Prize Committee of Basic Sciences, Dr. Shu Narumiya, Professor and Director of Medical Innovation Center at Kyoto University Graduate School of Medicine. I'm Narumiya. Nice meeting you. Lastly, Chair of Kyoto Prize Committee of Arts and Philosophy, Dr. Kiyokazu Washida, Professor Emeritus at Osaka University. I'm Washida. Nice to meet you. Now we start the conference. First, I would like to call upon Dr. Sakaki, Chair of Kyoto Prize Executive Committee, to announce the 2021 Kyoto Prize laureates. After that, achievement of each laureate is to be explained. Now, Dr. Sakaki, please. I will now announce the 2021 Kyoto Prize laureates for this year. The 2021 Kyoto Prize for Advanced Technology in the prize field of Information Science goes to Dr. Andrew Chi-Chih Yao. He is a computer scientist and his age is 74. His achievement is pioneering contributions to a new theory of computation and communication and a fundamental theory for its security. He is currently Dean of Institute for Interdisciplinary Information Sciences at Tsinghua University. But since 1975, when he got the PhD degree in the United States, for 30 years, he made outstanding research contributions at MIT, University of Stanford, California, and Princeton. Since 2004, he has been working at Tsinghua University. Next is the category of basic sciences. The prize field this year is life science, and the laureate this year is Dr. Robert G. Rader. He is a biochemist and molecular biologist and 79 years old. His achievement is discovery of the principle of gene transcription mechanisms in eukaryotes. He has been active for 35 years at Rockefeller University in New York in the capacity of Arnold and Mabel Beckman Professor for Biochemistry and Molecular Biology. But before that, he also made great research achievements at Washington University School of Medicine for about a decade. Lastly, arts and philosophy. Prize field this year is thought and ethics, and the laureate is Dr. Bruno Latour. He is a philosopher, 73 years old. His achievement is radically re-examining modernity by developing a philosophy that focuses on interactions between technoscience and social structure. He was professor at Paris Institute of Political Studies for 12 years and now is a professor emeritus. But before this institute, Dr. Latour made a remarkable achievement for 25 years at National Conservatory of Arts and Crafts and Center for the Sociology of Innovation, Paris School of Mines as an associate professor and later professor. Those are the 2021 Kyoto Prize laureates. All three are quite well and active today. This year is the 36th Kyoto Prize. We are very happy to note that all three laureates are excellent and very appropriate persons in the name of Kyoto Prize, which is now widely recognized as an international award. It was my pleasure indeed to have reported to you the laureates of this year in the capacity of chairperson of the Kyoto Prize Executive Committee. Thank you. Thank you, Dr. Sakaki.
Now, we'd like to explain the achievement of each laureate. First is the laureate of Advanced Technology, Dr. Andrew Chi-Chih Yao. Committee Chair Mr. Tokuda is explained. Now, Committee Chair Mr. Tokuda, please. Thank you for introduction. I am Tokuda, in charge of Information Science in Advanced Technology, and I'm going to explain the achievement of Dr. Yao. Dr. Yao's achievements are pioneering achievement in building the basic theory of information science, especially the communication complexity theory, which is one of the most important tools in computational complexity and the theoretical foundation for security based on it. It has a great ripple effect on the cutting edge of information science, such as security, privacy, parallel computing, big data processing, and quantum computation. If I try to raise the representative achievement, algorithm analysis, communication complexity theory, and security of cryptograph protocol, pseudo-random number test, and secure computing, and quantum computation. With the interest of time, I'd like to explain only representative achievements. First is the creation of communication complexity theory. An object in conventional computational complexity is extended to a system consisting of communicable objects such as multiple computers, and complexity of any calculation using the distributed data, here expressed by the function f, is measured using new and original communication complexity, such as how much communication must be done between these elements, what is the minimum number of communications. In conventional basic theory about communication, there is Shannon's information theory on efficiency of data transmission and coding. Dr. Yao's idea has extended the traditional theory of computational complexity to a comprehensive theory that includes the number of communications required for distributed computation between computational components. It is applied to the limit of circuit complexity, complexity analysis in parallel distributed calculation, data structure and stream calculation, and so on. In recent years, many computational theories are relying on it. Next is achievement on security analysis of cryptograph protocol. He has created a model called Yao model. As cryptography and cryptographic protocol become more and more complex, it is very critical to ensure strict and mechanical security. The Yao model established a formal method to prove security by a new mathematical technique in the early 1980s. This is a different approach from the traditional computational complexity, which is based on computational complexity, established a model that abstracts the message flowing in the communication path of the cryptographic protocol with symbols and makes them mathematically verifiable. This is a contribution to subsequent security certification. and this made a huge impact for the development of various mathematical models. Another achievement is random number test, which is important in increasing security of cryptography, and it is called Yao's test. There are pseudo-random numbers generated by a computer program, and they can be reproduced by giving initial value and algorithm. On the other hand, there are physical random numbers generated from random factors of physical events in the natural world. 1 and 0 are independent of each other. The probability of occurrence is equal, and unpredictability is guaranteed. The Yao test has established a method for efficiently determining randomness. Pseudo-random numbers are commonly used as an alternative to true random numbers in cryptography, so poor performance of pseudo-random numbers can adversely affect the security of the crypto system used. Finally, he has an achievement in the secure computing field, which has had a huge impact in the crypto field. In what is commonly referred to as secure multi-party computation, MPC, Dr. Yao illustrated the problem of Yao's millionaire problem and established the concept of secure two-party computation, and made a great contribution to secure MPC field. The Yao millionaire problem is a problem in which two wealthy people decide which is richer and which is without knowing each other's wealth. This is a method that allows parties to make calculations using each other's information while communicating with each other while keeping their information secret. It is possible to protect the privacy of each other. In 1982, Dr. Yao proposed a method of performing secure calculation with M participants, and in 1986, he devised Yao's garbled circuit protocol, which is now the basis of many efficient MPC protocols. As of 1987, it proved to be effective even if there were already attackers among the parties. As an application example of MPC, the effect of medical treatment is measured while hiding the medical data of the patient. The correlation between the disease and the genetic information is analyzed while hiding the individual genetic information, and the collision of multiple satellites while hiding the orbital information of the satellites. So it is possible to solve problems with great social needs such as risk analysis. These series of achievements by Dr. Yao have had a great influence and spillover effect on the field of information science and are truly suitable for receiving the Kyoto Prize. This concludes my explanation. Thank you very much, Chair Mr. Tokuda.
Next is category of basic sciences. Laureate is Dr. Robert G. Rader. Dr. Narumiya is going to explain. Now, in this year for life science of the prize field, laureate is Dr. Robert G. Rader. Let me explain his achievements. Please look at the chart on the monitor. As you know, our body constitutes of about 60 trillion cells, and there are many kinds of cells. This diversity of cells are formed with the regulation of gene transcription. That is a discovery of Dr. Roeder. In our body, cells have nucleus. Stimulus is given to nucleus, and within the nucleus, genetic code information is transferred from DNA to RNA. That is called transcription. Transcription is the information relay from DNA to RNA, and the messenger RNA goes out of the nucleus, and the protein is formed and that is expressing the lots of phenotypes. Therefore, regulation of gene transcription has been the big question, especially in the life science. That was the very basic big question. And our cells are different from the E. coli. We have the nucleus in cells. In the case of a human, 3.1 billion of base pairs are in existence. That means the DNA of 3.1 billion are in series. One information code is quite lengthy, and it's folded into the nucleus in compact way, and histone is the object. DNA is wrapping up the histones and stored in compact way. Therefore, our cells are different from E. coli. In eukaryotes, what is the regulation of gene transcription had been the big question. From the template DNA, the RNA is to be produced. That's the transcription. There are three types of RNA. Messenger RNA, which is coding the proteins. And the second is the ribosome RNA. Those are the components of the ribosome. And the third one is the transfer RNA that carries amino acids to the ribosome. And Dr. Rader, in 1965, that was 50-some years ago, did the experiments. The RNA polymerase's activity was tried to be explored. This was the first report from Dr. Rader. Doctor did the experiments, namely conducted the chromatography using gradient of ammonium sulfate when he eluted the fractions. Then he isolated 3 distinct RNA polymerase activities. Then the different sensitivity to the toxin of mushroom or localization in cells were utilized in his research to identify 3 RNA polymerase. Polymerase 1 will produce the ribosome RNA, polymerase 2 makes messenger RNA, and polymerase 3 will make the 5S rRNA, small RNA, and also transfer RNA. Therefore, he discovered the 3 polymerase for RNA in eukaryotes. Next, first and foremost important question is how they find the start site for transcription and make precisely the required ones. And Dr. Rader found that the polymerase alone cannot find the initiating point, start point. There is a requirement for another factor. He added the various kind of fraction of extracts from the nucleus. In the case of polymerase 2, 44 polypeptides are required to recognize the start point for transcription, and then transcription can be successfully terminated. That is the discovery of the pre-initiation complex, PIC. That means, as shown here, first of all, 44 polypeptides or complex will recognize the start site, and then RNA polymerase will be recruited, and DNA make a pair, so therefore that should be loosened, and then RNA will start the polymerized. Then from PIC, RNA polymerase will be released, and then initiation of the transcription will be allowed to go on. This is the mechanism that he elucidated. Also, as you can see, each cell requires the different type of transcription factors which are activated at a certain required timing. Then activating factor is necessary. Dr. Rader, as I said, made the experiments for the polymerase 3, and that will transcribe the 5S rRNA. However, polymerase alone cannot synthesize it, but TF3A, that transcription factor is added, then transcription can be activated. As I said before, for the differentiation of cells, this type of gene-specific transcription activator is required. Dr. Rader discovered the first example of this type of gene-specific transcription activator. Now we have found over 1,600 of those activators. As you know, Dr. Yamanaka's 4 factors are the one example of this type of transcription activators or transcription factors. And Dr. Rader also discovered the important finding on the next slide. For the initiation transcription, sometimes there is the mechanism of the 2, which has a great distance by several thousands of bases. Why can this happen? That was the question. And then he started a research and he found the mechanism that activator is working or bound to the sites, and PIC is bound to the promoters. There is a mediator that is a multi-protein complex bridging between the 2. Based on this, in the eukaryote, various kinds of factors are working. Even from a distant nucleotide sequence, gene transcription can be modulated. Lastly, Dr. Rader discovered the chromatin mechanism for the prokaryotes or the E. coli. DNA is naked. However, in eukaryotes, the DNA is wrapping the histone. And if that is too tight, then transcription cannot take place. Finally, Dr. Rader found the following. Nucleosome is the units. DNA is wrapping up the histone, and there's a necessity to loosen that binding, loosening the DNA binding, and then the PIC will be formed and elongation transcription will be made. With 80 or more of the purified polypeptide, he successfully reproduced a transcription in vitro. Therefore, Dr. Rader did the studies over 50 years. He discovered 3 distinct RNA polymerase in eukaryotes, and he discovered the general transcription factors. He discovered the first gene-specific transcription factor and mediators also that connects between gene-specific factors and PIC, which work spatially separated. And, as I explained, he elucidated the mechanism of transcription from chromatin structure. Therefore, he made a discovery of the principle of the transcription mechanism in eukaryotes. That's a great achievement. We truly believe that Dr. Rader is the very, very appropriate Kyoto Prize laureate. Thank you very much. Thank you very much, Dr. Narumiya.
Next, about the laureate in the field of arts and philosophy, Dr. Bruno Latour, Committee Chair Dr. Washida is going to explain. Now, Dr. Washida, please. I would like to explain about Dr. Bruno Latour, the laureate in the field of arts and philosophy. His achievement is titled Radically Re-examining Modernity by Developing a Philosophy that Focuses on Interactions Between Technoscience and Social Structure. Dr. Latu was born in Beaune, Bourgogne, France, into a Catholic family who had been wine growers for generations. He studied philosophy and biblical exegesis in Bourgogne University and earned his PhD from University of Tours in 1975 with a paper titled Exegesis and Ontology. Then he has taught in National Conservatory of Arts and Crafts, Center for the Sociology of Innovation in Paris School in Mainz, and Paris Institute of Political Studies. Now he is a professor emeritus of Paris Institute of Political Studies. Dr. Latu regards nature, human beings, experimental equipment as actors equally, describes science and technology as the operation of a hybrid network of these actors, and breathes new life into a view of science. And he has developed a philosophy to review modernity that is based on the dualism of nature and society. In recent years, he has also been attracting attention for his thoughts on overcoming global environmental problems that expose the limits of modern times. Let me try to summarize the achievements of Dr. Latour, which have led to the winning of Kyoto Prize. First, pioneering a new field of anthropology of science. Second, transforming the view of science by actor network theory. Third, proposal of new view of world and nature by reviewing modernity. Fourth, multidisciplinary activities. Now let me briefly explain about these achievements. While Dr. Latour was working on his dissertation, he went to Ivory Coast for the French civilian service, where he conducted anthropological research commissioned by French government. 2 years from 1975, he conducted anthropological study of laboratory of Roger Gilman, a physiologist who won the Nobel Prize in 1977. Based on this study, Latour and Steve Woolgar co-authored Laboratory Life, the Construction of Scientific Facts, which opened up a new field of science studies, anthropology of science. In anthropology of science, a researcher conducts participant observation and documents the activities of scientists ethnographically, and how he came to acquire the nature of the fact that the scientists found. This was a novel approach that had not been used in conventional science studies. Through anthropology of science, he showed that scientific facts are not created arbitrarily, of course, but are constructed through collective process. By showing association of various tools that can trace and visually show scientists' claim or others discussing that claim, the claim acquires the character of scientific fact. Dr. Latour worked with researchers such as Michel Caron and John Law at the Center for Innovation Sociology at Paris School of Mines in the 1980s to develop actor network theory, that is sociology theory that describes how science technologies are being researched. The term actor refers to anything that modifies the state of affairs by making a difference. And that includes not only humans who have been historically considered active subjects, but also non-humans which have long been considered passive objects. The network refers to the connection between those actors. In actor network theory, the production of scientific knowledge is described from the perspective of hybrid network operation that includes researchers' activities and equipment such as social systems, research funding, laboratory management, and laboratory equipment, and the experimental samples as actors. What is important here is that to consider not only humans or society, but also non-humans or nature symmetrically without assuming the asymmetric distinction of active or passive as actors. Such an actor network theory transforms the understanding of science and technology that has been established on the premise of the modern dualistic idea that confronts the inactive material nature and the human spirit and society that manipulates and deprives it. Dr. Latour discusses that global environmental issues are typical of cases showing the collapse of modern dualistic composition, and in order to solve the issues, we need to accept the perspective of Anthropocene seriously. Anthropocene is a term that refers to modern geological age at which human activity has brought about dramatic changes in the global environment. Nature and the environment, which have been regarded as stage sets, are emerging as actors on the stage, where only humans were considered to be actors. And now non-human actors are responding to human actions. That's how Dr. Latour thinks. The concept of nature as an object on which human subject works on, and the environment surrounding humans. These concepts are biased toward humans, and they are extension of dualistic ideas hidden in modern times that are causing environmental problems and climate change. The biosphere, which is a thin film of several kilometers above the surface of the Earth, on which we live, is a world of not only humans, but also various terrestrial beings such as animals and plants, climate, weather, and things. Dr. calls it as terrestrial, and he proposes that the political system and social system need to be rearranged by shifting to a new view of world and nature that is oriented from terrestrial. In order to share this new view of world and nature, terrestrial, with many modern people, Dr. Latour is engaged in a wide variety of activities, such as co-authoring papers with natural scientists and collaborating with artists as an exhibition curator. Dr. Latour's multifaceted activities, which have influenced a wide range of fields, such as business administration, geography, and political science, as well as anthropology, philosophy, and sociology through anthropology of science and actor network theory, provide an alternative mode of academic activities in the 21st century. This concludes my explanation of Dr. Bruno Latour, the laureate in arts and philosophy. Thank you, Dr. Washida. Now, we'd like to conclude the press conference of the Kyoto Prize laureates.